Hello, dear students. Today, let us learn the definition of circulation and Kelvin's circulation theorem for a continuum. Circulation around a closed curve is defined as uh, the line integral. Okay, the line integral over that closed curve C v dot dx. The vector v is the velocity dot dx. That integral is nothing but the circulation. The circulation around a closed curve denoted by IC, and that is nothing but the line integral v dot dx, where v is velocity and dx is the position vector of any point in that continuum. This line integral can be converted to a surface integral as surface integral S curl v dot n ds. And that curl v is nothing but the vorticity w or omega. Curl v, we know that curl v is nothing but what? It is the vorticity w or omega dot n ds, where n is the outward unit normal of the surface ds. And how the conversion of line integral into surface integral is by Stokes theorem. Okay, so the circulation IC is 0 if and only if, so when the LHS is 0 here, whenever we have that W equal to 0, W or omega equal to 0. That is, in other words, the circulation is 0 for irrotational motion. When omega is 0, that means curl V is 0. That means vorticity is 0. Whenever the vorticity is 0, such a motion is called irrotational motion. Circulation is 0 for irrotational motion. Now let us see what is Kelvin's circulation theorem for a continuum. Kelvin's circulation theorem for a continuum. So, the statement is this: if the acceleration is the gradient of a potential function, any scalar potential function, then the circulation around a material closed curve remains constant. So if the acceleration is the gradient of a scalar potential function, then the circulation around a material closed curve remains constant. That is a statement of Kelvin's circulation theorem. Let us prove this theorem for any moving continuum. Okay, now let us take a continuum which is moving, right? So what is the definition of the circulation? Circulation is given by, denoted by IC, and that is equal to the line integral over C. C is that material closed curve. Remember, material closed curve. V dot dx, where V is the velocity and dx is the position vector at any point in that continuum. Okay, we have to prove what? We have to prove that the circulation remains constant. That means we have to prove that this IC is constant. We have to prove that IC is constant. We shall take the time derivative of IC, and we prove that the time derivative of IC, of time derivative of circulation, is 0. So therefore IC remains constant. Okay, so we shall take now what? The time derivative. That to which time derivative we are going to take? We are going to take material time derivative. Okay, so consider the material time derivative of this IC. That is capital D by dt of IC, that is equal to capital D by dt of what is IC? We is substituted here. So IC is nothing but the line integral over the closed curve C V dot dx. That is equal to that is equal to this d by dt, which is outside, can be taken inside. That is by Reynolds transport formula. By Reynolds transport formula, this d by dt can be taken inside. Now, in the next step, we have the differentiation of the product, differentiation of the product v dot dx. So let us use the product rule for the differentiation. So differentiation of the first function, the second one as it is, plus first one as it is, and differentiation of the second one. Okay. Now, this one, the second part will become 0. Why this becomes 0? Let us see. Because this whole thing, right, can be written as v as it is, okay, dot also as it is. We can take that d outside, small d outside. We have capital dx by dt. And capital dx by dt, this is nothing but the velocity v. Velocity v. So that is nothing but now it is v dot dv. V dot dv. Right. Now let us consider. Now the integral is for both the terms. So for this also there will be integral. Now consider integral. Now consider the integral of this. So integral. Okay. So closed curve. So that is why that circle there. See, v dot dv is equal to the line integral d of v square by 2. We can write v dot dv as v square by 2, differentiation of v square by 2. For this way, we can put an arrow or without an arrow because v dot v is a scalar, right? Okay. So now, what is integration of differentiation of anything? That's nothing but v square. This has to be square here, not this 2, right? So v square by 2. And it is the closed curve here. The curve is closed. So the initial point and the end point will be same. So if I take the initial point as A, the end point is also A. Fine. So v square by 2, initial point A and the end point is also A. So that is nothing but equal to 0. Excuse me. Okay. So now, sorry for that. Now, so this part will become equal to 0. Fine. Followed. So what is remaining now? So what is our LHS? LHS is dic by dt equal to only one term on the RHS. So we have the line integral dv by dt dot dx. Let us call this as equation 1. Okay, let us call this as equation 1. Remember, we have to prove that the circulation remains constant. Okay, yes. Now, what is this dv by dt? What is our v? V is velocity, and dv by dt is nothing but rate of change of velocity. That's nothing but acceleration. So we have the integrand is our acceleration. What do we know about acceleration? What they have given? What is the statement? So statement, let us look at the statement again. It says, if the acceleration is gradient of a scalar potential function, then the circulation around a material closed curve remains constant. Okay. So what they have given? They have given the velocity, the acceleration. So given the acceleration, that is nothing but dv by dt, is gradient of a potential function. Scalar potential function. So dv by dt is equal to gradient of psi, where psi is a scalar potential function. Okay, so now using this. So let us use this in equation 1. So equation 1 becomes what? We have LHS dic by dt equal to, so in the place of dv by dt, you are going to put this gradient psi. So gradient psi dot dx as it is. And we know that this integral is equal to the line integral as it is, right? This part, that is, gradient psi dot dx is nothing but d psi. There's a d missing there. It is d psi. Fine. And what is integration of d psi? Is nothing but psi. Psi. And what are the limits? Limits are a and a. Initial point and the end points both are same because our C is a closed curve. Fine. So any function, if the upper limit minus the lower limit, if and both the limits are same, then it is always equal to 0. So we got the LHS. LHS is nothing but dic by dt equal to 0. What is IC here? IC is nothing but circulation. So rate of change of circulation is 0. That means IC is constant. Hence, Kelvin's circulation theorem. Very, very easy theorem. We shall go to take up a problem now based on circulation theorem. Okay, let us take this problem. Let us take up this problem. The problem says, show that the motion is circulation preserving. Show that the motion is circulation preserving if and only if, that is both the ways, right? Necessary and sufficiency. If and only if the acceleration is an irrotational vector. The acceleration is an irrotational vector. Very, very easy. So let us take, start with circulation, which says what? We know what is circulation? Circulation denoted by IC, right? That is equal to, so IC here equal to, line integral v dot dx, where C is the material closed curve, v is the velocity, and dx is a position vector at any point in the continuum, moving continuum. Okay. Now let us take the material time rate of change of this IC, that is the circulation. So capital D by dt of IC is equal to capital D by dt of this whole integral. Okay, that is by Reynolds transport formula, that d by dt is taken inside, right? V dot dx as it is. And d by dt of the product here, so using product rule, so differentiation of the first one, second one as it is, differential of the first one as it is, differential of the second one, using product rule. Okay, and the second integral will become what? So I can write down this d outside, So what now? Let me choose another color here, or let me draw. So this d. So in this term, we can take this d outside here, right? D outside, and capital D by dt x. Capital D by dx by dt is nothing but the velocity, right? So we are going to get v dv. V dot dv. V dot as it is, and this whole part will become, this will become dv. This will become dv. Okay, so now, and this integral again, will become what? So v dot dv is nothing but dv square by 2. You can put an arrow for v here, or without arrow also holds. And integration of d of anything is nothing but itself. So it is v square by 2. The first term is always same there. And this one between the limits, since our C is a closed curve between the limits a and a. So even when both the limits are same of any function will become 0. So this part will become 0. So this whole thing will be 0. Right. So there will be no contribution by the second term. So only the first term remains. So we have dic by dt is equal to integral dv by dt dot dx. Right. Okay. So now, so we have the line integral here. Now by using which theorem, how to convert, we have conversion from line integral to a surface integral. By which theorem? Stokes theorem. So using Stokes theorem, we can convert the line integral to a surface integral. So we have the surface integral S here, curl of dv by dt dot n ds, where n is the outward unit normal of the surface ds, by using Stokes theorem. Let us call this as equation 2. Okay, now let us take up the necessary. Necessary, what is given? If the motion is circulation preserving, that is given. And what we have to prove? We have to prove that the curl, we have to prove that the acceleration is irrotational vector. Acceleration is irrotational vector. Okay, so now, since the motion is circulation preserving, that means what? dic by dt is 0. Circulation preserving means what? The circulation is constant. Circulation remains constant. That means what? The differentiation, the rate of change of IC is 0. Whenever this is 0, what about curl of that? Curl of that. Now, okay, sorry. Now we have dic by dt equal to 0. Okay. So now using 2. So using 2. So this is 2 here. Using 2 implies that. So you have, this, the LHS equal to 0. So therefore, the integral will become equal to 0. So when the integral will become equal to 0, when the integrand is 0. What is the integrand here? The integrand is nothing but curl of dv by dt equal to 0. Curl of anything equal to 0, that means what? That vector is irrotational. So dv by dt is irrotational. dv by dt is nothing but acceleration is irrotational. Acceleration is an irrotational vector. Hence, necessary. We have proved the necessary. Very, very easy. Okay, now let us take up sufficiency. If the acceleration is, what is given for the sufficiency? If the acceleration is irrotational, that means what? Curl of that acceleration is 0. Now again using 2. So what is 2? So 2, okay, using 2, that integrand equal to 0. That means integral will become equal to 0. And the LHS is nothing but dic by dt equal to 0. Whenever the material rate of change of IC is 0, that implies IC is constant. IC is constant. That is, the motion is circulation preserving. Circulation is preserved. Circulation is constant. Circulation remains the same. Hence, the solution for the problem. Okay, guys, let us stop now. In the next class, we are going to prove 3 more problems based on circulation theorem.